Hello, I'm Professor von Schmohawk, and welcome to YU. So far, we have seen that raising any number to the nth power, where n is a positive integer, is equivalent to n copies of that number multiplied together. And that this is true not only for numbers and variables, but also for expressions. In this lecture, we will see what happens when the expression raised to a power contains more than one term. Let's start with a simple expression containing two terms, a and b, multiplied together, and raise this expression to some power n. As we saw, this is equivalent to n copies of the expression multiplied together. Now, since all the a's and b's are multiplied, and multiplication is commutative, we can rearrange the a's and b's any way we like. If we group all the a's and all the b's, we have n a's multiplied together times n b's multiplied together. The n a's multiplied together can be written as a to the nth power, and the n b's can be written as b to the nth power. So this expression is equivalent to a to the nth power times b to the nth power. So raising a product of two terms to a power is equivalent to raising each term individually to that power. This is true no matter how many terms there are in the product. For example, the expression could be a product of three terms, a, b, and c. Raising this expression to the nth power is equivalent to n copies of a times b times c multiplied together. Rearranging the terms, we have n a's, n b's, and n c's multiplied together, which can be written as a to the n times b to the n times c to the n. So we see that raising any product of terms to a power is equivalent to raising each term individually to that power. Now, what if a term in the expression has an exponent? For instance, let's say that instead of b, we had the term b squared. Once again, raising this expression to the nth power is equivalent to n copies of the expression multiplied together. Rearranging the terms, we have n a's, n copies of b squared, and n c's. As in the previous example, the n a's can be written as a to the nth power, and the n c's can be written as c to the nth power. The n copies of b squared multiplied together is equivalent to b squared raised to the nth power. As we saw in the last lecture, when we raise a term with an exponent to a power, we simply multiply the two exponents. This gives us b to the 2n. The rule for raising a product of terms to a power can be stated in a simple way. If we think of the terms without exponents as actually having an exponent of 1, we can just say that the exponent of each term in the expression is multiplied by the power to which the entire expression is raised. Notice that the terms which originally had no exponents end up with an exponent of n. So now we know how to raise an expression containing multiplied terms to a power. But what happens if the expression also contains divided terms? We can figure this out by using our rule for expressions containing multiplied terms and giving one of the terms a negative exponent. Multiplying each exponent by n gives us a term in the result with a negative exponent. If we move the terms with negative exponents to the denominators and switch the sign of the exponents to positive, we see that our rule works for expressions with multiplied and divided terms. So when raising any product or quotient of terms to a power, the exponent of each term in the expression is multiplied by the power to which the entire expression is raised. Now that we know how to raise any expression consisting of multiplied and divided terms to a power, let's try writing an expression with multiplied and divided terms in its simplest form. This expression consists of a product of three terms in the numerator, 2x squared, and z, and a product of two terms in the denominator, 3 and y squared. Remember that terms without exponents actually have an exponent of 1. Now, since this entire expression is raised to the third power, we multiply the exponent of every term in the expression by 3. As a final step, we can write 2 cubed as 8 and 3 cubed as 27. This expression is now written in its simplest form. Now let's simplify a fractional expression with positive and negative exponents raised to a power. Again, we temporarily add exponents of 1 to the terms without exponents. Since this expression is raised to the third power, we start by multiplying each exponent in the expression by 3. Next, we can write 2 to the 6th power as 64 and 5 cubed as 125. As a last step, we can move the term with a negative exponent from the denominator to the numerator and change the sign of the exponent to positive. We have now written this expression in its simplest form. Now, let's simplify a product of exponential terms raised to a negative power. Multiplying each exponent in the expression by -1, we get x to the -3 times y to the -2. If we move these terms to the denominator, we can switch the sign of their exponents to positive. This gives us 1 over x cubed times y squared. Now let's try the same problem, except we'll make the exponent of x negative. Now when we multiply the exponents by -1, we get x to the +3 times y to the -2. Moving the term with the negative exponent to the denominator, we get x cubed over y squared. Now let's see what happens if we take this result and raise it to the negative first power. Multiplying each exponent in the expression by -1, we get x to the -3 over y to the -2. Moving each term to the opposite side of the fraction and changing the sign of the exponents, we get y squared over x cubed. So raising this fractional expression to the negative first power simply flipped it upside down to create its reciprocal. In fact, raising any fractional expression to the negative first power flips it upside down, creating its reciprocal. As our last example, we will simplify a more complicated fractional expression raised to a negative power. Since this expression is raised to the negative second power, we start by multiplying each exponent by -2. Next, we can eliminate negative exponents by moving those terms to the opposite sides of the fraction. As a final step, we can write 2 squared as 4, and this expression is written in its simplest form. In these last few lectures, we have seen what it means to raise a number to any integer power. In the next lecture, we will see that it is also possible to raise a number to a fractional power.